Now, we can do this argument twice. After your third shot, there is a chance you could get as far as 300 yards, but it's quite small. And you're most likely to be at 150 yards because 50 yards a shot. And your actual distribution of probabilities where you're likely to be begins to take on this kind of shape. You know, they progressively are getting smoother and smoother and spreading themselves out. And after 4 shots, we'll go one more distribution yet. Your most likely position is to be at 200 yards, and your probability is distributed over a total range of 400 yards in a way roughly like this. And if we could calculate, there we go again. I'm getting to be a habit. All right.
You all right?
Yeah, we're okay.
Okay, very good.
Nothing bad has happened. We're still on the air.
You gotta stop these attention-getting slapstick. It's very cheap, Marty. This is supposed to be a show appealing to an intellectual audience, and
Yeah, well,
anyway, we're glad you came through it.
yeah. Well, let's get back to the discussion now. Look, if we could calculate all the areas involved in these distributions, then we would be able to solve a problem directly of figuring out where the guy's likely to be. Because, look, here's 50% of the guys make it after 2 shots. And if we could figure out what proportion of the area of this total curve was in this tailwise section here, and maybe it would be 90% of the people were over here, and we said 90% of the people made it after their 3rd shot, then we could add up all these probabilities and we could calculate an average. And when I first did this problem, that's exactly how I did it. I solved for these areas using calculus. These things happen to take the form of what the technical term is convolution integrals. And the nature of these calculations is suggested by this trick with throwing of the dice. But
You're talking about the area.
yeah, the areas. Yeah.
But what's the name of that curve to begin with? The one after the triangle?
Oh, then the one after the triangle. Well, what name do you think it is?
Gaussian or normal or?
Well, is this Gaussian?
I don't think so.
Well, this shouldn't be Gaussian either, but they're getting closer to being Gaussian. With each successive thing, they get more and more closer to what you call your normal distribution, your bell-shaped curve, or your Gaussian distribution. And an amazing fact of statistics is that whatever initial distribution you begin with, if you compound it on itself in this way by repeating it on itself successively, as you go down, it doesn't take very long before you begin to get very, very close to what's called your perfect Gaussian distribution, where the functional form is given by e to the minus x squared. And this result, that a distribution compounded in itself tends to approach a functional form of this general type, I think is known as the central limit theorem. But I'm not sure about that, because I looked up the central limit theorem and I couldn't tell what it meant, but it's got to mean this. If it didn't mean this, it should be this. So anyhow, this is the perfect way of solving it, but we want to try and do it without calculus and without doing convolution integrals. So we're going to try something a little different. Basically patterned after this kind of argument. And using elements of this dice concept. What we're going to do is say we got a dice with 2 sides on it. Or you could say it's an ordinary dice with 6 sides, but it's only got 2 numbers on it. It's got 1s and 2s on it. 3 1s and 3 2s. So when you throw the dice, you 50-50 chance of throwing 1 or 2. And we're going to ask how many times on average you're going to throw it before you go as high as 3, before you cumulatively get up to 3. So you could throw 1 on the first shake and then 2 on the second shake, and that will get you there in 2 shakes. You couldn't get there on 1 shake. You see, it's an analogous problem. We're going to start with this for our first analogy. And we're going to say, how far are you going to get? 1, 2, 3, 4. And after your first shake, you're either going to be on 1 or you're going to be on 2. So you still didn't get to 3. We're asking the question, what does it take to get you up to 3? So no one gets there on their first shake. But on the second shake, the people that were on 1, for sure, they get at least this far, and maybe they get this far. But the people who were on 2, well, some of them got here, and some of them got here. So there's 2 guys that would be sitting on 3, and 1 guy would have shaken from 2 and gotten up to 4, and 1 guy would still be struggling along here. But by the time of the 3rd toss, this guy would have made it. There's 3 ways you could have gotten to 4 squares, because 2 of these guys could have gotten here by throwing a 1, and this guy could have got there by throwing a 2. Now, as far as getting to 5 squares, there's a lot of ways you could have got there. This guy could have thrown a 1, or this guy could have thrown, either of these guys could have thrown a 2, so they could both be there. So there's 3 ways you could have got here. As far as covering to the 6th square, only guy would have got there is this guy if he had thrown a 2. So this is the distribution of locations after 3 shakes. You might recognize it as famous triangle known as
Pascal's triangle.
Neil knows it, of course. Pascal's triangle. You've got your 1s, 1, 2, 1, 1, 3, 3, 1, and I won't go into the reasons why you generate it here. There's a lot of reasons why you'd expect this kind of thing to happen. And of course, Pascal's triangle, you know, if you carry this through and look at the distribution of numbers once you get down to the 10th row, it's an excellent approximation of a Gaussian bell-shaped curve. So it's a very analogous problem. Let's just evaluate it. How many shakes does it take to get up to the 3rd step? No one made it after the first shake. 3/4 of the guys made it after the second shake. And the remaining 1/4 of the people made it on their 3rd shake. Total is 6/4 plus 3/4 equals 9/4, which is the average number of shakes, the average number of shakes of the dice to make it to the 3rd square. So we got it, 9/4. Now, of course, this doesn't answer the problem of the golf.